Welcome to UVU CS3060 Lecture 3.2, where we actually start working with processes on a system, creating, managing, and exiting processes, and seeing how they run through their various states. So the operations that we will see on processes include things such as process creation, process termination, and we'll talk in the next few slides what some of those operations are. Now, when it comes to creating a process, a parent process will create children processes. So parent process can actually have 0 or more children processes. Those children processes can also have processes, child processes of their own. And it actually forms a tree relationship. In most systems, processes will maintain that tree relationship for the business of administration of those processes. Every process is going to be managed via a process ID. A parent process will have its ID, and each child will have a separate unique ID. Parent and children will share some resources. There are different ways of sharing resources. We can have situations where both parent and child share all resources. Parent and child share only a subset of the parent's resources. And the parent and child share no resources whatsoever. And when we talk about resources, process resources include things such as the program text section, or the global data, the read-only and read-write data, the heap, and the stack. Sometimes we can have processes that execute at the same time, and we will deal with those processes in assignment 2. But we will also have situations where we can tell a process when we create it that the child will be able to run, and then the parent will receive status on the child as it's terminating. Here's a representation of processes under Linux, and we can actually see the same basic setup if we take a look at our Linux server. There's a program called PS_tree. PS_tree shows us processes and the parent-child relationship between them. Right now it's showing a lot of systemd processes. These are processes inside of a system, or inside a Linux system, that act as services. Let's take a look at the process IDs. If I use the -P, now it's telling me process IDs. You can see there are lots of different process IDs here. You can see here is my PS_tree running at process number 6445. It was actually generated or created by my bash shell, which is running as process 6305. My bash shell is running because I used SSH to come into the system, and the SSHD spawned different processes so that it could create the bash process. There is one very important process on this system. This is process ID number 1. We call this the root process. Sometimes you'll hear it referred to as the init process. In this case, it's the systemd root process. On Linux, process number 1 is the first process executed by the operating system kernel after the operating system boots. So when the operating system boots, process 1 is created, and everything else is a child or grandchild of process 1. When process 1 terminates, when that process ends, the system goes either into a reboot or shutdown state. The operating system kernel recognizes, hey, the only process I ever execute has completed, I must be done as a kernel, and it resets. We'll talk a lot more about process number 1 as we continue. Please remember that this is a critical process within any operating system. If we go back to our slide, you can see here this init process, process 1, and everything else is a child process off of that. So how do we create a process? Well, in order to create a process, we have to use a system call fork. Now, the fork system call does one thing, and it does it very well. It creates a new process. That's all it does. Notice it says nothing about a program. It creates a new process, but it continues the same program for both processes. We call this area, we call this the address space. The child has a duplicate of the parent's address space, which means if the child has a copy of the parent's address space, the child also has the same program loaded into that address space. So both parent and child, once the fork is executed, are running the same program. Now that's troubling to a lot of people, so I like to demonstrate what in the world I'm talking about. Let's come back to our shell, and I'm going to go into a directory here, and I'm going to create a program. First, before I go into the program, let's take a look at the fork API. Here's the fork system call API. There's 2 includes that we're going to have to use, sys_types and unistandard. But the fork API takes no parameters. There's nothing that you need to tell fork. All you need to do is call fork, and it will create a child. It will return a process ID. Now this is very important, and I'm going to go ahead and page down so we get to the return value, because I want you to understand what the return value of fork is. On success, the process ID of the child process is returned to the parent, meaning that the parent will receive a value that represents the new process ID of the child process. Okay? But the child process will receive a different value. The child process will receive 0. So, when we call fork, we must capture this particular value. If we don't capture this value, we won't know if we're the parent process or if we're the child process. There is, of course, a failure value that we should check for. So let's go ahead and use this fork API. We're first going to just run it as we'll capture the value. So I'm going to go ahead and create a source code new proc. We're going to include our 2 header files. First, actually, we're going to always include standard IO because we want to do formatted output. We're going to include unistandard.h, and we're going to include sys_type. Create our main function. We're not going to use our input parameters, but we put them in here just in case we need them. Now, I can go ahead and print out my parent process has started. All right. Now let's go ahead and capture the child process ID. All right, with fork. And remember, it takes no parameters. Now the first thing we need to do is check to see if it is negative. because if it's negative, we need to produce an error. We can use p error because the error variable is being set. Fail to start the process. And we'll return 1. Otherwise, we can go ahead and say printf fork returned %d cpid return 0. So simply, we're printing out a line at the beginning, we're calling fork, and then we're printing out a line after the fork and exiting. So let's go ahead and see what we get. I'm going to go ahead and make new proc. It builds. So let's go ahead and run new proc. And you'll see we print out that first line, parent process is started. It then prints out 2 of the fork return lines. This is simply because when fork was called by the parent process. But when fork returned, it returned in the parent process, where we got 6480, and it returned in the child process, where we got the number 0. When those 2 values were received, they were stored in a variable, and then they were printed out by the 2 separate processes. The 2 processes had 2 values at that point. So that is how to create a child process. We can do this again if we want to. Let's go ahead and just simply copy this code and paste it. And I'm going to do child process ID 2 fork. Is it less than 0? If not, we'll say second fork returned. Now, before I actually build this, I want you to consider what this program is going to do. One process prints out this first line, then fork is called. After fork returns, how many processes are running? If you said 2, you're correct. 2 processes are running. Both processes check for an error value. Both processes print out this fork output. How many processes are executing this second fork statement? If you said 2, you're correct. 2 are going into are executing this fork instruction. If 2 are executing, the first one is going to return 2 processes. The second one is going to return 2 processes. So what is the total number of processes that will be running after this second fork call? If you said 4, then you're correct. We should see 4 of these second fork return calls. 2 of them with 0 and 2 of them with a number. So let's go ahead and build it. How about make new proc? Some people just don't know how to type. And we run it. Now, some very interesting things happened with this particular program. We have the parent process, which prints out once. Then we have this fork returned and a numeric value. So ask yourself, was this printed statement printed by the parent or the child? If you said the parent, you're correct. This is the output of the parent process. The child process has not reached its print statement yet. It has not been scheduled. Now there is a second fork returned. This second fork returned was printed after the second fork was called by the original parent. It received a number back, which indicates that this is the first, it is the parent process, the original parent process, after it's called its second fork. Up to this point, the first parent, the original parent, is the only process that's been scheduled. And very likely, after it printed out this second fork message, it terminated. It went to a terminate state, which meant that the first child that was created finally gets scheduled, generates its particular child, and then the other two children are printed out. This shows you that the scheduler can do some strange things. Sometimes we'll get different results. Now consider for a second what happened here. We had the parent print out, the parent returned from fork and printed out its number, but then it didn't print out its second message. It actually was put on the ready queue more than likely, and the first child was scheduled. What you're seeing here is that the scheduler will make decisions on processes and when they run that sometimes vary considerably between processes. The rule here is you cannot rely on a process to run in a particular order when you have other concurrent processes running. If you expect process 0 to do something before process 1, then you have an invalid expectation. There are things you can do to fix that, but in general, do not expect two concurrent processes to run in a specific order. The scheduler will make choices that may not make any sense to you whatsoever. Now, let's talk a little bit about the next instruction that we see here. Fork, as you saw, was just simply creating new processes. It is not actually doing anything with the program code that is in memory. In effect, the fork creates a new process control block so that after fork is done, two process control blocks now exist and can be run on the CPU. Those process control blocks share many similar attributes, such as the registers, including the program counter. They're the same, they're copied between process control blocks, as well as the memory location. Those are pretty much identical. The child is an identical copy of the parent's memory. Open file handles are also copied from the parent to the child. The only thing that should be unique between parent and child is its process ID. Now, creating a process is all fine, but how do you get another program to run? Well, generally what happens is you first call fork, and then within the child, and you'll be able to identify the child, you call a second function called exec. This exec is actually built to load a program into memory and provide arguments to that program. The parent, on the other hand, will call a function called wait. Wait will cause that parent process to be put onto a waiting queue while it waits for the child process to load its program, execute the program instructions within that process, and then that process calls the exit system call. When the child process calls exit, wait in the parent resumes. So let's give this a go. Let's see if we can make this work. So we return back to our code. Let's go ahead and modify this a little bit. I really don't want all this nonsense. I've proved my point. All right. Now what I want to do, after I've created my child and tested to see if it's successful, I need to check to see, is this process the child or the parent? If it's the child, then I know the process ID will be 0. So I know this is the child process. And so within the child process, I can perform my exec call. Now, before I write this exec call, let's actually go look at what the exec call does. Let's pull up its man page. Man to exec. There is no manual page for exec. So maybe at this point I need to do apropos exec. Oh my goodness, look at all the stuff that we have here. What is exec? So there's execute a file, the exec in 3. So let's do man page 3 of exec. Now, something to realize, exec is actually a fairly complicated call into a library function that makes system calls. It actually calls what is known as the clone the clone system call API. The exec call takes unistandard, and we're already including that. But what we want to do is we want to perform one of these variants of exec. Notice they all start with exec, but they have 1, 2, or 3 characters following exec. We need to choose between these different variants. The first variant is the L variant. The L variant, there's 3 different variants of it. The L variant actually takes a variable number of parameters, kind of like printf. With printf, you do a format string, and then you follow it with 0 or more variables depending on the format specifier. Well, in this case, this exec L will take 0 or more parameters that follow this particular program that you're loading. All of the variants have one parameter in common, and this is the path to the program you're loading. This must be a path to that particular executable file. This particular path here has to be a path that is either absolute or relative and points directly to the binary. The exec LP treats the first parameter a little bit differently. In exec LP, what it's doing is it's taking the path that you specify, and it's actually searching through the system to find the executable you're looking for. This might be handy for us if we're trying to load a program at a particular location, but we don't know where that location is. And I'll demonstrate both. The exec V is similar to L, but instead of taking a variable number of arguments, it actually takes an array of strings. Now, I do want you to notice the name of this array of strings. Yes, that is argv. In fact, each one of these exec APIs that you're calling here are actually forming, after the path, are forming the argv that will be used by main inside the process. So this is the string array that you're going to pass to the main function, and it will figure out argc by counting the number of elements that are in your array. This will just simply count the number of arguments you've passed in. Let me demonstrate. So I'm going to come in and edit my program. So I need to exec here. I want to exec the program ls. You're familiar with ls. It lists files for me. Now, I'm going to start by breaking my program. I'm going to perform exec L. Now, exec L, of course, takes the name of the program, or the program file you're going to load. It then takes an argv. It takes your argv arguments, And I'm going to put, for the first one, the name of the program I've launched. If you remember, argv sub 0 is the name of the program that is launched. And I'm not going to send it any more parameters. Now I'm also going to put a printf here. I'm actually going to do p error because it returns a error no. Able to launch ls and return 1. Okay, so that's my exec. So make new proc and run new proc. Now you'll notice that it says it's unable to launch ls, that there's no such file or directory. This is because my code used the exec-l. Now if I use exec-l, whatever path to a file I type in here, it must be able to find. Is ls in my current working directory? No, it is not. Where is ls? Well, there's a nifty little program called which. If I type which ls, it tells me that ls is located at bin ls. So let's go into my code, and instead of just plain old ls, let's go ahead and tell it /bin/ls. I'm not going to change argv sub 0. There's a reason for that. I'll discuss it here in a bit. But now if I go ahead and make new proc and run it, you'll notice that it says parent process is started. It then brought me back to my prompt, but after my prompt it printed out the list of files. What this means is that my parent process has actually executed ls, but it was allowed to finish executing, and bash returned control before my new child process was allowed to execute ls and be scheduled. We can fix this. If you remember back here in this particular diagram, that we have a fork and that the child performs exec. Well, in our situation, fork allowed the child to be created, but it didn't allow the child to perform exec. What it did was it caused the parent to exit and terminate. It did not wait for the child. What that means is we can actually prevent this from happening, where our parent terminates before our child terminates, by performing a wait operation. Let's take a look at the wait. See if it's in system calls, and it is. It requires systypes and it requires syswait. The wait function requires one parameter, a pointer to an integer variable. We're told down here that let's scroll down a little bit more. It actually tells us that the wait status can be null. Right here it says if it's not null, it will return status. If it is null, it won't return any status. So I'm going to go ahead and just simply pass it null. But I'm going to do this in the parent process. So else, if I'm not the child, I'm definitely the parent. I'm going to wait. And I don't really care about the status. I will in a short while, but not right now. So we'll save this. We'll make it. Oh, it's not going to build, or at least it's going to give me a warning. I forgot the syswait header. So I'm going to go ahead and put that in here. Found include syswait.h. Make new proc, and there it is. Now you'll notice that it printed out my parent statement, and then ls was able to execute, and then my prompt, and that will be consistent every single time. So if you're the parent process in your code, you need to make sure you're waiting. Now let's discuss a little bit about this wait. This wait can actually return a response. And we know that if, let's say for example, we have an error, that we return 1 here. So let's go ahead and get a response from our wait. And we do that by sending a reference to an integer variable. That way wait can put in the exit return of our child process. And then we'll print it out. Child returned %d response. So I'm going to make this. And I'm going to run it. Well, the child, when it errors, that child process should be returning 1, but for some reason we get a value of 256 back. This is simply because, if we go back to the wait man page, the wait man page tells us that this particular status that we're getting, the wait status, stores status information in the int. This integer can be inspected with the following macros. The integer actually contains more information than just how the status. We can see whether it exited normally. We can check the status, and we'll actually use this macro, the wExitStatus macro, to see what the exit status is. We can even identify the type of termination. Did it leave a core dump? Is it stopped? Lots of different things can come back from that wait. But let's actually get our exit status, not just simply all the data that's in there. So I'm going to go to new proc. And instead of just simply printing out response, I'm going to print out exit status of response. Basically, wExitStatus translates the values within this response and gives me the exit status data. So now, when I run my broken program, how about we make new proc? It'll say the child returned a 1 for an exit status, which is exactly what we were looking for. All right, let's fix our process creator. Now, going through and finding that this particular program is in bin ls tends to be a bit of a trial because it might not always be there. It may be in a different location, which is why there are different variants of the exec. Exec-L has an exec-LP. That P means that whatever program you're searching for within the first argument, it's actually going to search the system for that program. So let's go ahead and save this, make it. Now I'm going to echo a value of a environment variable called path. This path variable has several different directory paths separated by colons. You'll notice that one of these directories is bin, which is where ls is found. What the exec-LP does is it looks through each of these paths one at a time and for an ls. If it doesn't find one in the first, it looks to the second, and it keeps searching until it finds ls. So if we run new proc now, it finds it for us, and our child return value is 0. This way, we don't have to type in the full path to a particular program to be able to load it into a process. So my suggestion is that you go ahead and use exec-LP for your particular process or program loading APIs. Now, what if I want to add more parameters to this? Well, I can go ahead and add more parameters to this function. So I'm going to go ahead and do a -L, so it does a long listing for me. Remember to include the null when you do this. You have to have the null as the last parameter here. So let's go ahead and save this. Make new proc. And run it. And now, when we run this, ls isn't just the file names, it's the long listing. It's using parameters now. Now, one thing that you'll notice is every time I want to add a new parameter, I have to change the function and recompile. This is kind of a chore. Inside the source code here, we've been using the exec-lp. Now, one of the problems with exec-lp is anytime I want to change these arguments, I'm going to have to recompile exec-lp. But there is a way to manage the exec without having to recompile your code every single time, and that's using a structure. So I'm going to create a character array, a pointer array. We'll call it exec lsargv, or the lsargv array, and we'll go ahead and put our argv in here. So we'll start with ls, that's argv sub 0. We'll do -L, we'll do -A, and then we'll terminate it with a null, just like we were doing below. Now, instead of exec-lp, I can use exec-vp and replace all of this with the array that I declared as a variable. So if I write this, build it, and run it, now we can see that we're calling ls, but now we're calling it with different arguments. And now it is a simple thing to just programmatically manipulate a character string array to add or remove parameters as necessary. Another upshot from this is that here in line 19, because it's argv sub 0, it's the program I'm loading, I can just simply do this, delete this, and do ls argv sub 0. Now exec-vp is completely dynamic, entirely relying upon the content of this character array, which can be changed programmatically. Just to verify it, make new process, run the process, and it runs successfully. The exec API is very powerful, and its primary purpose is to load a program and provide that program's main function the necessary arguments to get started. This is where argc and argv come from when you run your main program. Let's come back to the slides. So that should explain a little bit about how fork and exec work in tandem here. When you perform a fork, you generally fork to parent, which waits, or you fork to child, which performs an exec, and then the exec launches a program that it will eventually terminate. Something very important to understand. If exec is successful, if exec successfully loads a new program into memory, then it is no longer running the code that it was running before exec. This is the code that called exec, but after exec, it's a whole different set of instructions. And in fact, your process is no longer your program's process. That process becomes the process of that program. So this is a demonstration. You certainly can look this up in the slides if you want. It pretty much shows you everything we've done. It creates a child by calling fork. tests for an error, checks to see if it's a child, performs exec, and then goes ahead and waits on the child. Windows does things slightly differently. Windows has a create process, and create process is basically fork and exec in one function. It loads the program into the new process space, sends whatever parameters you want to send to it, helps with the memory allocation, all of this. And then that parent process, the child process is on its own. The child process this function does not return either as a parent or a child. This always returns as the parent. The child will be executed in its own space. In this case, the parent can wait for that particular child to complete. Now, process termination is very important here. Now, when a process executes its last statement and then tells the operating system it wants to finish, it calls the exit system call. Now, what the exit system call does is it actually deletes the memory of that process and then saves the status data for that process for the parent to gather up. All the process's resources are deallocated by the operating system when wait is called. A parent may terminate the execution of a child process using an abort system call. There are reasons why you might want to do this. We're not going to go through this right now, but this is a particular system call where a parent has control over the child. So, some operating systems do not allow child processes to exist if its parent has been terminated. If a process terminates, then all its children must be terminated as well. We call this a cascading termination. This is not how it happens under a Linux system. Under a Linux system, if a parent terminates, then actually any child processes for that parent are actually moved to a different parent. And in the case of Linux, that different parent is process number 1. We call these processes where the parent terminates, we call these processes orphan processes, meaning that the parent has died and the child has been orphaned and sent to process number 1. Of course, process number 1 is always going to exist as long as the kernel is running. When process number 1 terminates, the operating system terminates under Linux. On the other hand, if a child terminates and there is no parent to wait for it, if a parent is not waiting for that particular child, that child will remain in a zombie state. This usually only happens if the parent process continues to run and does not orphan the child to process number 1. If the parent process continues to run, that child process will continue to exist as a zombie until either the parent process calls wait or the process number 1 calls wait. Because eventually the parent process will quit, and when that parent process quits, that child will be moved to process number 1, init. When it does, the child process becomes an orphan, whether it's a zombie or not. And then process number 1 performs the wait operation on that orphan child. Thus, a zombie will be gathered by a init eventually. Sometimes you have programs, such as browsers, that actually are multi-process browsers. The Chrome browser is an example of this. The Chrome browser actually has 3 processes running. It has the browser process, which is this outside element that controls all the combination of the windows, controls the tabs, usually controls disk and network I/O, etc. You also have the renderer. The renderer processes are each tab. Each tab here represents a different URL, and that URL runs in a processor sandbox, which restricts disk I/O and network I/O and tries to minimize the effects of security exploits. In this restricted environment, if a web page tries to do some funny business, it's not allowed to, and the process could be terminated, or the process just simply will error out. There are also separate processes for plugins, and usually you have plugins over here on the right-hand side that perform additional functionality for various web pages. So this is an example of a program that does multi-process operations. This has been a discussion of how to work with processes, Lecture 3.2. Thank you very much.